And so now we'll go through the second and third laws of thermodynamics, which deal with the definitions of entropy. And so this is the second law of thermodynamics, written out here. And as Lord Kelvin said, no process is possible in which the sole result is the absorption of heat from a reservoir and its complete conversion into work. It's not always perfect. In fact, it can't be perfect. And so this is an example from reversible isothermal expansion. If we have this expansion, we see that, we take the V final and divide by V initial, take the natural log, multiply it by the temperature, number of moles, gas constant, we get the amount of work. But the temperature hasn't changed. So we have the internal energy change is 0 because we have a constant temperature. So delta T is equal to 0. And therefore, the amount of work that the system did is the opposite sign but equal magnitude of the heat involved. And so this is what we're saying. This is not actually achievable, but we will say it is for our calculations. But if this were achievable, you could have a perpetual motion machine that took in heat and did work perfectly.
So 100% efficiency.
100% efficiency. And this is just saying it's not achievable. It's just not achievable, yeah. And so this is essentially the second law of thermodynamics is what tells us that perpetual motion machines are not achievable. What would be an example of a perfectly efficient engine? And that's what I said about our automobiles. If we burn that gas fuel in the cylinders and the temperature of the exhaust was 0 Kelvin, not just room temperature, but 0 Kelvin, it had sucked every bit of heat out of that gas and pushed the piston as far as the expansion would go, and then completely cooled the gas down to 0 Kelvin. And so this order to disorder is spontaneous. And we see this all around us. It's something that we know about. And we see it even in the bouncing of a ball. So the height of a ball decreases as it bounces because that ordered motion is converted into disordered motion. And you can think of it too as energy levels, right? That there's translational motion, and when it hits the surface, that unidirectional translational motion is turned in and lost to all these other little energy levels, these vibrational energy levels in the surface. And you're not going to get that energy back into the ball. And so it's dissipated because it's for an instant in contact with another surface. And that kinetic energy is now turned into other forms of energy, random energy, heat, so the surface heats up. But it's fun to interact with this kind of effect. And you can play with materials, like we have these rubber balls, which are fun to play with. Watch this. They look the same, but something's different about this one. So, let's just make me laugh. So what would it be different about this ball than this ball?
Elasticity.
A harder material.
Why do you say harder? And elasticity, they're kind of related to each other.
It's not bouncing the sides. It's not transferring in energy as well.
Yeah, it sounds harder too. Yeah. But you would think, though, if it was harder, it would be rigid and it would bounce, right? Because it couldn't. I mean, this one is delivering some of its energy into the table, but retaining some too. So it's bouncing back. This one is not bouncing back. So where'd all the energy go?
Into the chest.
But they both weigh the same. So they're probably turning the same amount of energy. I mean, they're probably delivering the same amount of energy into the desk, no matter where it goes.
So this could be the consistency of the material.
It's got to be something different in the materials.
Density?
They feel they're about the same volume and they feel the same weight. That might be a little heavier, but
this one's like almost like hollower.
yeah, I don't know what we're feeling, but there's definitely a difference. And I'll pass them around and look. They used to be both exactly the same shininess. but this one has gotten duller. So now I can tell which one's going to bounce and which one's not. The dull one is the one that's dead. And I think, again, I haven't analyzed these, but you can play with this kind of what they call energy storage in a material by changing how the polymers cross-link. And this is a polymeric material, so it's like a ball of yarn at a molecular level. And if that ball of yarn absorbs its own energy when it hits, it does that. But if it's able to store that energy and get it back, then it does this. So what way could you keep a polymer from absorbing energy by the yarn threads slipping past each other?
More hydrogen bonds. Bonding goes
Hydrogen bonds are okay, but you could make covalent bonds.
Oh.
You know, and those would be more rigid. And so that's called cross-linking. You've got a polymer ball of yarn, and if you cross-link and pinch those polymers together with covalent bonds, then they become more rigid and they won't slide past each other. They have a restoring force. And so this one is probably more cross-linked than this one. This one hits, and that ball of yarn, those polymers slide past each other and have lost that energy to friction and all kinds of things. So it's just something you can do. So this one would have a different heat capacity, a different entropy. It's got more accessible energy levels than this one. And so it's not just the material that it hits, but also the hardness of the materials. Now, you could, in theory, go from disorder to order. It's not impossible, but it's very, 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 and add on a mole of varies, improbable. Because I've been around objects sitting loosely on desktops my whole life, and then I'm not saying it's impossible. I couldn't say that it's impossible, but it's improbable because I've never seen anything spontaneously hop off the desktop. How many times did I drop these balls on the surface? I mean, a lot, right? Okay, so I've stored enough energy to bring this ball to this height in this desktop. I've put all that energy into the desktop. I'm adding energy to the ball by lifting them up, and I'm dropping them, and I'm storing that energy in the desktop. You know, it's just wait for them to pop up. The energy's in there, but it's just really improbable for it to go from disorder to order and cause motion in one direction. So all that energy that I've put into it has been lost in the tiny little quantized states of this desktop. And so once again, we use the surroundings to decide when a process is ordered or disordered, and that's work versus heat. We're not going to just have spontaneous, order jump out of a table like this. And so this another sort of restatement of the second law. The entropy of an isolated system increases in the course of a spontaneous change. Now I highlighted that in red for an important point. This is the isolated system. If it's isolated, then you have no access to the surroundings. So if your system is not isolated, then you can have a decrease in entropy and a spontaneous change. Okay. But an isolated system's entropy will increase in the course of a spontaneous change. Like if you put water in the freezer and it freezes, you've decreased the entropy. And it froze. It was spontaneous to freeze. But you're defining water as your system. And so it was spontaneous that it froze, but it's not an isolated system. Where did that heat go from the water in your freezer? Yeah, what's the environment? In our house, it's the kitchen. That's where our freezer is. Yeah. And so the entropy of our kitchen increased more than the entropy decrease in the ice. So the water decreased its entropy and froze, but the heat was pumped out and heated up the air in the kitchen. And that entropy, when you compare that entropy rise to the entropy drop in water, the net entropy is going to be positive. So it heats up my room a little more than it took out of the water to make ice. The simplest isolated system to conceive of is the universe. The whole universe is moving towards disorder, and the entropy is increasing, but the interesting thing is that it's still very low. We still have pockets of order. When I say order, I mean things that aren't just a gas, separated at near infinite values. We have stars and planets and ice cubes and trays inside my freezer. Okay, we have a lot of ordered things in this universe, and when I say that's a huge deal, this very thing by itself is one of the supports for like the Big Bang theory that the universe had a beginning. Because if the universe was infinite in the past, then all the entropy would have dropped to lower, and our planets would have ablated, our stars would have burned out, everything would have cooled down. We have a hot universe that implies that we have a lot more entropy than we would have if it was infinite in the past. And so this is one of the things that physicists call the entropy problem of the universe. This is when they were trying to decide, is the Big Bang telling us what we think it's telling us, and that time and space had a beginning? Or, how do we deal with this entropy problem? We have really a low entropy for an infinitely old universe. So getting back to smaller systems, so we have this reversible isothermal expansion of a gas. This is how you would calculate the entropy. It's that change in heat divided by the temperature. And so we know that for isothermal reversible expansion of a gas, that the change in internal energy is zero because it's isothermal. And so that Q is equal to minus W. That calculation for W was minus nRT, the natural log of VF over V. So we lose the minus sign, and we take the derivative with respect to temperature, and it was just temperature to the first power, so that's gone. And so this is how we calculate the change in entropy for the isothermal expansion of a gas. So very similar equations pop up all the time in these calculations. Let's look at the third law of thermodynamics. This is probably my favorite because it makes calculations so easy. At 0 Kelvin, all the excited state energy has been sucked out of a substance, and so the partition function, you know this from your stat mech, has been reduced to 1, and the natural log of 1 is 0, and so the entropy goes to 0 just using a statistical argument. And so this kind of lines up with that third law statement that you read in textbooks. The entropy of a perfect crystalline atomic substance is 0 at 0 Kelvin. The main ramification of this is that we can now use tables. We have a reference point. It seems arbitrary, but it's really not, knowing from statistical mechanics that the partition function is going to go to 1 at low temperatures. And so that's going to naturally take that entropy down to 1, down to 0. But the ramifications of this is that we can have standard entropy tables. You look in the back of your textbook, or you can Google it online and look for thermodynamic properties of substances, and you'll see standard entropy values, and you'll have the different substances listed, and you can look up their standard entropy values. They're based on this definition. So anything above 0 Kelvin and anything in any other state other than a crystalline atomic substance, so a thing that's bonded, is going to have a higher entropy. And so we can look at that. Let's look at some of the entropy of phase transitions. So we have evaporation and condensation of steam. Think about those two processes. So evaporation, you've got water going to steam. You have condensation, you have steam going back to water. You're going to have a huge change in entropy. Which is going to have more entropy, steam or water? Steam? Why do y'all say steam? Tell me more.
They're just everywhere.
Think back through your stat mech. Even though we're not going to calculate it, why would steam have more energy levels accessible than water?
Temperature.
Okay, yeah, you've raised the temperature to make the steam. Okay, but let's say the boiling point, you're right at the boiling point. So you go from water at 100 C to steam at 100 C. So temperature hasn't changed. But what if you had to do to get it to go from water to steam at 100 C?
Raise the pressure.
Oh, raise something. Let's say you're at atmospheric pressure. So you're adding in energy, right? I jumped on raise and I was like, raise the energy. But you're putting in joules, right? You've got a pot on the stove, it's at boiling, and that heat's still going into the water, but the temperature's not changing. Okay? And you're converting it from liquid to gas. But the entropy is a measure of the number of energy levels populated. And think about the translational energies. Think of a particle in a box. This is a simple way to think about it. You've got a water molecule surrounded by liquid, and it's got a box that's, the size of that little water cage. And now it's steam. The box length is the room. And so those number of accessible energy levels has gone up an enormous amount. Melting and freezing for water. Again, which one what do you think is the highest entropy? Ice or water? Water, okay. How can we mentally think about this? Again, ice is locked into a particular motion. It can't even really rotate. It can shake, but it can't rotate. It gets into liquid state. It can rotate. It can tumble. It can slide past nearest neighbors. Okay, so it's got a larger box, if you will, to move around in. And so this entropy change of a transition is just the enthalpy of that transition, and we measure enthalpy of vaporization, enthalpy of fusion or freezing. And so freezing and condensation are exothermic. And so the signs will tell you also what's going on. So delta H is less than 0. If you're freezing or condensing, you're giving off heat. Okay, and so you have a negative entropy change. And then if you have melting or vaporization, you have a positive sign on enthalpy, and that's causing an increase of entropy. Let's look at some plots. This will kind of put it into perspective here. So you could start at absolute 0 and calculate the entropy change as you raise the temperature. You have this whole region here where it's a solid, and then a liquid, and then a gas. And so if you're sort of you're looking at the entropy rise, you get to this transition where it's melting. Notice the temperature doesn't change. You're at the melting point or fusion temperature, and the heat that you pump into the system causes an increase in entropy, but you're still at that same temperature. Then you're warming up the liquid, and entropy is increasing, and then you reach the boiling point, and you pump in joules and joules and joules until you turn it all to steam, and then you have the entropy change of the gas. That plot here is represented by this long equation. Whatever temperature you happen to be at, you can calculate the entropy that you're at. You can work your way all the way up to it, taking into account any phase transitions that you have, and look at the heat capacities that you're using. You're using the heat capacities at constant pressure. So that's typically what we operate with in the lab. Let's look at another plot. This was assuming those heat capacities are constant, and for most of our work they will be. Really cold temperature work, they're not. So this is for oxygen. This is the experimental data for oxygen. So let's start up here at room temperature at 300 Kelvin, 298 Kelvin. We're off the screen here, but notice these are the heat capacities. That's what's being plotted here. The heat capacity for oxygen, which has a boiling point that looks like it's around 90 Kelvin, actually has an activated vibrational mode, because oxygen is pretty heavy, 16 grams per mole each. So we have the 3 halves R, The rotation added in 5/2 R, 1 vibration added in 7/2 R. Then we get here to that liquid transition, and the heat capacity jumps up here to almost 50. Again, that's the whole molecules moving around in the liquid, providing more what we would call pseudo-vibrational modes of whole molecules, larger masses, and so very close energy spacing, huge partition function. And then we have the solid 1, the solid 2, and the solid 3. And this is probably the first time you've been introduced to multiple solid phases. I don't know, maybe some other courses you've had, but you many times don't just have one solid phase. If you think about what can happen if you're packing things into a solid matrix, you can have them randomly associated, which would be an amorphous solid, or you can make different kinds of crystals. And you saw from your oxygen dimer lab, you can have T-shaped, you could have linear, you could have tetrahedral, and those are typically the solid phase transitions. You might go from a square rhombic structure to a tetrahedral structure. And there's a slight change in volume, which gives you a slight change in partition function, which gives you a slight change in heat capacity. And so let's just finally end up with the simplest calculations. These are going to be the ones that you'll have to do in this section of the course most frequently, and that is using the thermodynamic tables. So if we have a reaction like this with hydrogen and oxygen making water, we can look up the entropy values in the table for the reactants and the products. And it's just the sum of the reactants minus the products. This should have been done in Chem 2, I think, where you do standard reaction enthalpies, standard reaction free energies, and entropies. The pure elements for entropies must be included. They're not included for enthalpy and Gibbs energy. And so we go to the tables and look those up. Notice we're talking about liquid water, and so we want this number here. That's the most common mistake, especially with water. You can see water, you come down here and grab the gas value incorrectly and do the liquid, or the liquid value when you should be doing the gas. You've got to look at the equation that you're actually working with. And then oxygen here and hydrogen. Going back to that equation, we see then that we need 1/2 mole for the oxygen, 1 mole for the hydrogen, and then the liquid water term. So the product is water, so we have 69.9 minus the hydrogen value minus 1/2 of the oxygen value. And so we have this entropy change. Notice it's negative. So we've gone from gas to form water. This is definitely a spontaneous process, though. This is how we take the space shuttle up to space. That big tank that the space shuttle is strapped to has 2 big containers in it, one with liquid oxygen, one with hydrogen. I don't think I got the high pressure enough to liquefy the hydrogen, but it's definitely hydrogen and oxygen going into the main engines on the space shuttle. So that's a spontaneous process, but it's a decrease in entropy. And so we'll find out next time when we talk about Gibbs energy how that can be. Because spontaneity is not just governed by entropy. It's governed by the total amount of entropy compared to enthalpy. And it releases so much heat that it becomes spontaneous. And so then this is per mole of hydrogen or per mole of water, but it's per 1/2 mole of oxygen. And so for the oxygen term, you'd have to double this amount to show what it would be for a mole of oxygen. So that's all we've got. See you Wednesday.